Today's event marks the third installment of Crossroads of Ideas, which is a program series presented by the Illuminating Discovery Hub at the Wisconsin Institute for Discovery. It was developed collaboratively with UW-Madison and Discovery Building partners. Crossroads of Ideas brings together campus experts and community members to explore thought-provoking topics at the intersection of science, society, and the arts. Since its launch in 2014, the series has been a cornerstone of public programming at the Discovery Building, fostering dialogue, curiosity, and connection across disciplines. We are delighted to have you here in person, given the weather, and online. Before I say more about this evening's event, we'll take a moment to acknowledge the land that we occupy here at the Discovery Building. The Wisconsin Institute for Discovery at UW-Madison acknowledges that it occupies the ancestral lands of the Ho-Chunk Nation, known as Teejop, which means four lakes. The Ho-Chunk have stewarded this land and its waterways, Mendota, Monona, Wabiza, and Kegonsa, since time immemorial, maintaining deep cultural, economic, and spiritual ties. We honor their sovereignty and the shared strength of standing together with all First Nations of Wisconsin. Tonight, in honor of the International Year of Quantum, we're here to explore quantum science and the role it plays in shaping the present and the future. To help us, we have two amazing scientists standing right there, Dr. Albarghouthi and Dr. Matthew Otten. We will hear first, we'll hear a little bit more about the research that each of them do here at UW-Madison. We'll have then a conversation and time for Q&A session at the end. I will briefly introduce them and then let them talk about what they do. Dr. Oz Albarghouthi is an associate professor in the Computer Sciences Department. He studies automated synthesis and verification of programs. He received his PhD from the University of Toronto. Dr. Matthew Otten is an assistant professor of physics, and his theoretical and computational research focuses on achieving practical quantum computing. He received his PhD from Cornell University. So let's start with Oz. You can tell us a little bit more about your research. You can stay there if you wish. Okay. Yeah. Yeah.
All right, yeah, thank you all for coming. I guess I was going to just give a brief history of quantum computing as seen by a computer scientist, and then you'll hear from the physicist. So you'll get both sides of the question, and then we'll have a fight. So that's how it works, right? So I'm a computer scientist, so I study computers and how computers work and how algorithms work and how software works. And computer science is ultimately built on bits. Bits is the fundamental unit of information. A bit can be 0 or 1. It can be on or off. So like a light switch, you can turn it on, you can turn it off. And everything around us when we think of computers is digitized as ones and zeros. So for instance, if I want to send a message, an email, I take each letter and represent it as a sequence of zeros and ones. So I can decide that A is 0001 and B is 0010 or something like that. And everything around us is just built upon this fundamental principle, and somehow it works. Somehow we have iPhones, and somehow we have the internet, and somehow now we have AI that talks to us in natural language. So it's pretty amazing. And all you have to do is build a system that can turn on and off the light switch many times per second. And boom, you have a computer and you have everything around us. So it's kind of incredible. And some computer scientists study how to take zeros and ones and stack them really neatly and on hardware, or store them and have them reliably there for a very long time. Some computer scientists study how to send zeros and ones for very long distances. And some computer scientists study what can you do with zeros and ones if they are given to you and you can manipulate them. So that's the story of computer science so far. quantum computing adds a wrinkle to the whole thing. I mean, ultimately, it's based on quantum mechanics, and quantum mechanics is weird. So it allows us to not only have a zero or one, but we can have a combination, or what we call superposition, of zero and one. So you can have a part zero and part one, and you can have negative parts as well. So it's kind of very confusing, both mathematically and intellectually and practically confusing. Um, so you can have a quantum bit that is in both states at the same time, both zero and one. What does that mean? What can we do with it? This, of course, relates to the, probably many of you have heard of Schrodinger's cat, that is both sitting in a box and is both dead and alive until you open the box and look at it. So here we have the same idea, but instead of cats, we manipulate bits, and these bits can be both zero and one at the same time until we look at them, and then they decide what they want to be. So it's pretty fascinating. So that's kind of the first thing that arises if we decide to build computers based on the fundamental rules of quantum mechanics that have been around for about 100 years or so, give or take. So that's number one. The other interesting thing is that you can entangle information. So I can have some information, quantum bits on my device, like let's say my cell phone, and another person on the other end of the world, and this information can't be entangled. If I do something on my device, it immediately happens on their device as well. So that's the notion of entanglement, and that was very confusing to physicists, and probably is still kind of confusing. So once you start thinking of computers with these principles as opposed to just zero and one, you get all those interesting properties. And for a very long time, computer scientists were not sure what to do with that. Like, okay, great, we can do something more complex and messy than zero and one, but so what? I mean, we have the internet and we have AI. What more can we get? So that's the big question. Like, should we spend time thinking about these weird things and what they can do? And yeah, for a while there was no good answers. There were many attempts. In fact, one of the first kind of attempts to use quantum information or computing was a proposal to use it for money. Because with money, a big problem is forging a bill. I can take it and copy it and create a new bill, and now I have $200 instead of just $100. And some people decided to use the laws of quantum mechanics to build something that is non-forgeable, because the rules of quantum mechanics tells you that you cannot take a piece of information and copy it in the same way that when I send an email, I send it to many people and they each get a copy. That is not allowed by the rules of quantum mechanics. So that's one way where you can use it. Very useful, but really hard to do in practice. Um, but then the big breakthrough happened in 1994. So in 1994, a mathematician by the name of Peter Shor discovered that you can do integer factoring, meaning you can take a number and find its prime factors really efficiently on a quantum computer. Okay? So you've probably all seen prime factoring in middle school, probably, where you take a number and find its factors. So for example, the number 21, its factors are 7 and 3. Those are its prime factors. 7 multiplied by 3 gives you 21, and they're both prime numbers. It turns out that if you give me a very, very, very large number, let's say thousands of digits, then it's really, really hard to factor that efficiently on a computer. If you combine all the computational power we have in the world, it might take thousands or millions of years, depending on how big an integer that you can give me. So this algorithm demonstrated that quantum computers can actually do factoring efficiently. Okay? So that was the first indication, or compelling indication, that quantum computers are something that we should study as computer scientists. And it's interesting because the year this was discovered was 1994. And another thing happened in 1994, which is Netscape released their browser. And I was pretty young in 1994, but the other day I was talking to a distinguished scientist in my field, and he was telling me that he was having lunch with other scientists, I believe at Bell Labs at the time, and Peter Shor's algorithm had just come out, and the Netscape browser had just come out, and the discussion on the lunch table is which will be bigger, quantum computing or the internet. So far the internet is winning, but we never know where things are going to go in the future. So the reason this algorithm is interesting is not only it shows that a quantum computer can do something that a normal computer cannot do, at least not do efficiently within a reasonable amount of time. This problem of integer factoring is at the heart of cryptographic systems. So when you send a message on the web or you send an email, it is encrypted, so it's scrambled, and then only at the destination is it decrypted. And the reason is you don't want someone to catch the message halfway through as it's flying through the air or going down the wire, and look at it and read your personal information. And all of this is built on mathematical puzzles. And in this case, the mathematical puzzle is integer factoring. So if someone finds your scrambled message and they want to read it, they have to solve a very large integer factoring problem. So Shor's algorithm demonstrated that if we can build a large enough quantum computer, then we can solve this efficiently, and therefore security will fall apart. So it's a big, big question in computer science: is how can we circumvent these loopholes in our cryptographic systems? Because you can read people's information, you can access their bank accounts potentially, you can cryptocurrencies fall apart, etc., etc. The other stuff that probably Matt works on and studies are simulating quantum mechanics and quantum materials, and that could be very useful for things like drug discovery and materials discovery and so on. And I'll leave him to talk about it. So currently, we're building quantum computers. I don't build them. I study them and think about them. But we're at a very interesting state. If you look at where am I? The computer science building. It's over there. That's the new one over there. There are thousands, maybe more than thousands, maybe tens of thousands of computers in that building. But they're all the same. Like, it's literally the same thing. Whether it's a phone or a computer, it's a bunch of transistors packed in a small chip. And with maybe some are larger than others, but ultimately they all work in the same way. If you look at the physics building, and I think it's over there, is it? Yeah, somewhere there. There are maybe like 3 or more quantum computers, and they're all very different. So when you think of quantum computing, it's at a stage of a Cambrian explosion where there's so many different, very interesting ideas, and each quantum computer has its unique quirks and properties and underlying hardware. So it's a very different world. And as a result, if you want to use a quantum computer, you need software to use that quantum computer. And with normal computers, the hardware moves very, very slowly. So the software doesn't have to, catch up, or we don't have to change it every day. Whereas quantum computing is moving really, really fast in many different directions because people are trying all sorts of ideas. And as a result, the software has to keep up. So what my research group has been looking at is approaches for automatically constructing such software as these devices change and are modified and new ideas come up from physicists and other engineers. And it's kind of an interesting time and a convergence where we have quantum computing and we're trying to build quantum computers, but we also have the power of artificial intelligence where we can do a lot of these things automatically and speed up the scientific process. So this is what I work on, and this is what I'm excited about, and that's pretty much it.
Good. I'll go stand over there too. Great. Thank you, Oz, for explaining everything in such good detail, leaving me a very interesting follow-up. So I think following up on, so I'm Professor Matt Otten. I'm in physics. I'm a physicist. I also have a joint appointment in chemistry. I do a lot of things using classical computers. You think about quantum computers. I tend to say I'm sort of a bad physicist, also a bad chemist. I'm a terrible electrical engineer. I'm not a good computer scientist, but quantum information science sits at the center of all of those things, right? So the physics of the qubits is, as Oz said, we don't really know what we're going to build these big, fancy quantum machines out of. So we have to know a lot about physics to really get the qubit right, whether that's picking up an individual atom, one single atom. There's sort of 10 to the 23rd in a piece of material. We pick one up and we store that using lasers or magnetic fields, and that is 1 qubit. So it's sort of astonishing that we can pick up one atom. And we have to do that a million times to build, say, a useful quantum computer that could factor prime numbers. We also build qubits out of very, very, very cold superconductors. So if you Google a picture of a quantum computer, you also see these very beautiful chandeliers. Those are actually cooled to temperatures that are some of the coldest in the universe, so that we can finally control this quantum information, because the physics of the qubits, they don't really want to exist unless they're very, very cold. These different systems are all described by physics, but what we want to do with those, say factor prime numbers or simulate chemical systems, we have to understand the target applications, whether that's using a quantum computer to understand how to create fertilizer. So one problem of much interest to the quantum computing community is simulating a molecule called nitrogenase. Nitrogenase is a biological molecule, it sort of exists in the soil, and when your plants need fertilizer, they need ammonia, they need nitrogen to grow. That happens just naturally in the soil, and it's pretty efficient. However, humans want to farm at scales far beyond just your garden, and so we have a very, very expensive process called the Haber-Bosch process. It takes about 3% of the total energy across the world to create ammonia, to create fertilizer, so that we can farm at the scales necessary to feed the whole world. It takes a lot of energy for us to do that, but nature just does it on its own, and we don't understand that yet. And the understanding of that, it's a quantum mechanical process at its base, that this small molecule that exists in the soil, many of them, they are performing some process that's defined by chemistry, which the quantum mechanics is the rules of chemistry. If we understood that, we could perhaps design a better catalyst, design a process that's much cheaper and more efficient, and that's what we think the power of quantum computers will allow us to do. Quantum computers, being naturally quantum, we have strong evidence both from intuition and also from things like computer science that tell us that a quantum computer would be able to simulate that molecule and allow us to design a better process, to get understanding of the physical world, but then put that into action to have a positive impact. My research spans both of these sides, the physics of the qubits and also the applications thereof. About half of my time is spent talking with really good physicists who build these exquisite experimental devices, which we call quantum computers. And I work very closely with them to try to make their devices perform better. Right? Each individual qubit is a very complicated, hard experiment. We need, it turns out, millions of them to do the types of calculations that would be necessary to simulate nitrogenase or to factor these integers. And we need to make each of those qubits perform really, really well. And so really understanding the physics of the qubits and optimizing them with classical computers is one part of my research. The other half of my research is thinking about how we would use these. What are the types of problems we would want to solve, whether that's a chemistry problem for nitrogen fixation, or that is factoring large integers, or simulating drug discovery. We work very closely with domain experts, application experts who, this is the problem I would want to solve. This is the thing that would change the world, change my field, which would be scientifically or industrially relevant, but I can't solve it with today's computers. I've tried really, really hard and I can't do it. We work with them to figure out what are the specific algorithms, quantum or classical, but mostly quantum algorithms, what would be necessary to solve their problem. And then we work all the way down to asking how long would that take on a set of physical qubits. So if I wanted to solve the problem of factoring a prime number, I would need 1,263,264 qubits, and they would need to run for 17 hours, 36 minutes, and 27 seconds. That is the type of calculation that we do, because turns out we don't have 1 million qubits today. Your bank statements are still safe. We have 100 or 1,000 qubits. But the rate of development of these platforms is accelerating, and it's not. Some of that is happening, say, over in the physics building. We are building small quantum computers there, but these are devices at the scale that we need to do these utility scale calculations are going to be the size of a Costco, for instance. And they're going to take a lot of space, and they're going to be very costly. And so we do work here in Madison and at various academic institutions to help accelerate that by understanding the basic physics. But it's really industry that's going to take and build these really big devices. And there are several companies, including two who have very close ties here in Madison. Colab, which is across in the old Service Memorial Hospital. They have quantum computers being built there. It's a startup company, as well as Inflection, which traps individual atoms. They have offices downtown. Those are two amongst dozens of companies, which span from startups of 10 people to giants like Google, Amazon, IBM, and Intel, who are all in this race to build these quantum computers. The prize at the end of the tunnel is factoring prime numbers, drug discovery, materials discovery, simulating physics and chemistry. The cost is millions of qubits, but the race is on. And many of these companies have public roadmaps, many of them publicly traded companies. They say that by the end of the decade, they will have something at enough scale to be interesting and useful. As an academic who isn't trying to get VC funding or keep my shareholders happy, I'd say that's a very optimistic target and is perhaps a little more sociological. By the end of the decade sounds a lot better than next decade. But there are many companies that claim we'll be there, and there's large investment from both private equity, publicly traded companies, as well as national initiatives, both here in the United States and in both countries that we're adversaries with and that we're partners with all around the world are investing in this technology. I guess that is my introduction, and maybe we have some moderated questions now.
We do, but you guys did a really good job answering most of them. So no, that's great. So I think we covered the main difference of a regular computer versus a quantum computer, the bit versus the qubit. What do you think the biggest challenge is in trying to build a useful quantum computer?
Maybe I'll start. It's a little bit of a physics question. Each qubit is really, really hard to build. This year's Nobel Prize, for instance, was awarded to the technology that goes into one of these qubits, a superconducting qubit. John Martinez, who's associated with Colab, the startup company that's across the street, he did this kind of foundational work in the 1980s to build the unit called the Josephson junction that goes into superconducting qubits, and it's taken 30 years to go from that groundbreaking experiment to having 100 performing qubits. And if we look at the development of classical computers, these things sort of accelerate. So perhaps we're going to be a lot faster to going from sort of 0.5 to 1 to 100 to hopefully a million. Um, but building each individual one was really, really hard. We are quite good at that now. We can reproducibly build one or a few, 100 across many different platforms, many different physical instantiations of this. But building a million of something is a lot harder than building one of something. And one way to see this is right now when we build one of something, one superconducting qubit, we actually have to put several wires down coaxial cables, just normal wires. It doesn't look that different than what you plug into your wall to watch TV. We have to put a lot of those down into something that's about the size of this tall, this wide, a foot in diameter. If I want to have a million qubits, I need millions of wires. It's a lot of wires. We do millions of wires in a regular data center. There are lots and lots of wires. These are problems that can be handled, but they become kind of large-scale systems engineering problems that we physicists like to think about simple things. And we really need electrical engineers, mechanical engineers, and other engineers to come in and sort of engineer devices for us at scales that are far beyond an academic lab. That's why the industry is taking this up. But yeah, I would just say that we're in a scale-up phase, and just taking these little single atoms or these superconducting qubits or single electrons, which we use for the qubits, and making them reproducible a million times to get to the scale that's necessary to do utility scale, these big calculations, which are valuable in and of themselves. The problem is sort of scaling up.
I don't think I have anything to add. Thanks. Okay. I'm not a physicist.
So, Oz, you mentioned that you work on the software part of quantum computer. With classical computers, you take the physical properties for granted, while the physicists and engineers are trying to scale up. Are the computer scientists really talking to them to try to understand how to best design the software? Is it really, does the software depend on what's on the other side, or are you trying, I'm just trying to understand also what is the direction that the software development is going? Does it depend on the hardware?
Yeah, we try to talk to the physicists, but they don't answer our emails. They're too busy. They're tangled in wires. No, I'm kidding. So if you look at traditional computing, we've built a very, very big stack of abstractions that we don't think about what's happening under the hood anymore. Like if you go talk to any computer science professional or computer science professor, they won't be able to tell you how a transistor works or what a transistor even is most of the time. But they work at a much higher levels of abstraction, and this process happened over many years. Where right now, if you want to program a computer, you typically write programs in a very high level programming language, and in recent years this has become English, so you can literally tell the computer what you want to achieve, and then it generates code that gets translated all the way to electric signals that run on a computer. So it's a very long process going from my English utterance all the way down to that. Whereas with quantum computers, we're still at the level of laser pulses and stuff like that, and the programming languages that we have are very, very low level. So there's a very big gap, and that's why researchers like Matt think of an end-to-end pipeline of going from a big problem like nitrogen fixation, I guess, or something like that, all the way down how to simulate it on a quantum computer. And we still don't know how to go there. We need the expertise of someone really, really smart to go all the way. And we still don't know what the right tools are. There are so many software tools out there, but it's kind of like a messy a messy toolbox of that is not very coherent, and there's no like clear process of how to go from problem all the way to implementation on hardware. So it's still at the infancy, and as I said at the very end, the fact that quantum computing is arriving at a time where AI is becoming quite mature could be an accelerant in that space as well, taking us from the high level problems, the scientific problems, all the way to implementations without having to go through the drudgery of building all everything along the way. So we'll see what happens.
So how many years do you think we will need before we have a useful quantum computer? Matt alluded to that a little bit.
Yeah.
And what will the useful quantum computer be used for?
It's a great question. It's a question that I think about in my research all the time. And to be a bit pedantic, you have to define pretty much every word in that sentence. And one of the most important words is useful. Useful is a really multifaceted concept. One could argue that some of the devices we build today are already useful because a professor used it to write a grant proposal and got $100,000 funding to do his next experiment. So that was used, but that is not usually the scale we think of quantum computers. We think that they're going to sort of change the world. And so you really have to level up your definition of useful to, one version of this is, does the calculation that you do on the quantum computer, either factoring a number or trying to discover a drug or simulate nitrogen fixation, is the value of that calculation, does it exceed the cost of building the device, right? I said it's a Costco-sized building that's going to have lots of features in it. What does that cost? Does it cost 100 million? Does it cost $1 billion? It's sort of a data center scale enterprise. What are the calculations that you could do on that device, and how much are each of those worth? And so part of my research is asking those questions, which makes me sort of a bad economist as well. I don't understand the economy very well, but I have to think about whether calculating this ground state energy of FOMOCO, some really technical problem, which is very specific because I'm going to run it once and I'm going to get an answer. Was that worth the time spent on that device? And as far as we can tell, it will be worth it, that the value of, say, drug discovery and the value of nitrogen, finding new catalysts to turn carbon dioxide into methanol for carbon capture, those are very valuable problems which have societal impacts that are quite big. And we think quantum computers are the only way to solve some of these problems. That, to our best understanding of AI and machine learning, for all its ability to draw pictures of dogs and cats, it doesn't seem to be able to do quantum mechanics at that scale with the certainty that we would need to go and build a drug based on that. Quantum computers, computer scientists and physicists seem to agree that they can really solve these problems in a way. Okay, so that didn't answer the specific question. That got to the definition of useful. So when I think that a really good benchmark date is 2033, sort of far enough away that you guys will forget that I said that date. Close enough that it sounds like sounds really useful. It also turns out to be the date of a big initiative by DARPA, the Quantum Benchmarking Initiative. It's a big funding program that DARPA has to ask this exact question. And they said the very specific question behind that is, can we build a utility scale where the value exceeds the cost? Can we build a utility scale quantum computer by 2033? So they set that date, and there's a lot of good scientists and engineers and program managers and product managers there who are thinking, and so they set that benchmark date, which is a little bit later than what many of the industry players will tell you. So 2033, if I have to give you a date, I'm going to tell you 2033. And then what it will be used for, very early on, I think it'll be used for science type questions, discovery questions, drug discovery, new catalysts for carbon capture, new battery materials, these sorts of questions. Factoring integers is actually really a valuable task because that could break encryption schemes like Bitcoin and both my bank records and national secrets. But the actual value of that is rapidly decaying because the National Institute of Standards and Technology, NIST, is already releasing post-quantum cryptography standards. And so you can steal my bank statement from today, but my bank statement a year from now might be post-quantum cryptographically secured. And then, by the time we get to that 2033 Q day, as some have called it, the most encryption might be beyond the reach of quantum computers. That doesn't mean there weren't valuable things that were harvested now to crypt later. So some sort of state secret might have been valuable to keep it held until that time when a quantum computer could get there. But as the time goes on, the value of each of those decays. I think that's an answer. Long-winded. I think you should give a date too.
Yeah, I guess. Yeah, I'm quite I'm a contrarian, so I'm gonna go with 2034. So, I think probably like in the next 10 to 20 years. I think that's my estimate. But I think, and I agree with Matt that probably the first wave of applications is going to be scientific. But once we have quantum computers that can be used widely to some extent, perhaps by university students, and I think the emergent applications from there are going to be pretty wild because if you look at just the history of computing, every time a new platform shows up, the kinds of things people discover that it can do are way beyond imagination. Even if you go back to say 2007 and you look at the Steve Jobs' announcement of the iPhone, he just did not know what he was talking about. It was a very brilliant presentation, but he said, I give you a 3-in-1 device, a phone and a web browser and an iPod. And but then no one thinks about it this way. It's become like this critical infrastructure that we have, and everyone has a phone and everyone uses it, and it's incredibly powerful device. So the way we ended up using it was quite different from how we envisioned. AI is another very different example in the sense that it's based on ideas that go against our intuition that comes from statistics. Meaning that the base intuition tells us that we couldn't build such gigantic neural networks that run things like ChatGPT under the hood, but people discovered that they could. And there's no theoretical foundation under the hood that says that this will arise, meaning the machine can speak English and summarize documents and solve exam questions better than me and my students combined. And much faster. So all those emergent properties will not be discovered until we have those machines and we can play with them and play with them at scale, meaning so many people, smart people across the world can fiddle around with them and discover what they can do. So I'm excited about that inflection point when people can get their hands on quantum computers.
So do you think there'll be a day where the public is using a quantum computer without knowing? Well, they're programming something, and
yeah, it's a great question. I think with the rapid development of AI and going towards, as Oz alluded to, programming in English, not programming in C or Fortran or COBOL or whatever old language you might think of. If you're just sort of, Star Trek, computer, I'm about to fall into a black hole. Do a calculation and save me. You might imagine that there's some dispatcher that the AI agent just decides we should run this on a quantum computer. It's the best for the task. Or run it on a classical computer. And It might not. It's probably not going to be a quantum computer in your phone because it's sort of a big, complicated device, and it's hard to imagine we could get them small enough. People said that about regular computers, so to mark my words. But you with cloud compute and the access of internet and rapid networking, you might just sort of press a button on your phone, say, do this calculation, and it figures out to route it to a quantum computer in some crazy envisioned future of really wide access to these devices.
Yeah, I mean, I guess, we could get to a point where that's the case. I mean, we already are very far away from our devices normally. Like, most of our data is in various data centers that most of us will never probably see. You can't just go and visit a data center, which would be a nice thing to do, actually, if they let us. So I imagine, I mean, I guess a big industrial vision and governmental vision is to have quantum computers playing along with other computers, for example, using them to accelerate AI workloads, which it's unclear theoretically whether they can help or not, but there are people who are working on or claiming that they could be useful. So we could live in a future where, when you say talk to something like ChatGPT or ask it to do something for you, under the hood it's combining both normal computers and quantum computers. We never know. That could be a future. And again, with the rise of AI and automation, you could imagine a lot of scientific questions being discovered or solved under the hood by AI agents that are using quantum computers as their experimental testbed to test their ideas. So that's another possible direction. Yeah.
I think it's time to open it to questions from the public.
Oh, thank you. Great presentation. And I laughed at mentioning Fortran and COBOL in my era. Give us a sense of energy consumption. So let's say 2033 or 34 happens. What will that Costco-sized device consume compared to, the data centers Google and Meta and everybody else is building today? And also give us a sense of the hardware choices that people have made that have failed and been successful.
Yeah, great question. So on power consumption, it really depends on the specific device, but to sort of generalize, it turns out each independent operation is sort of cheapish, but there's a lot of infrastructure around it. So these very, very cold systems, superconducting qubits, have to be kept at near almost absolute zero temperatures. That requires very specialized helium and liquid helium. So you really need a huge, like half your Costco is just cooling. And that takes a significant amount of power. I mean, we do a lot of cooling on classical computers as well, but this is just a totally another level. If you're building it out of neutral atom systems, where you're trapping single atoms, which is really phenomenal, you have a lot of lasers, and laser pointers run out of energy really fast, and I need a lot of very powerful lasers. And so I wouldn't expect the first versions of this to be any more energy efficient than a data center. But we're at really early points in the technology, and if you look at the way that classical computers rapidly lowered their energy consumption or kept the energy consumption sort of fixed and just rapidly increased their processing power, I'd say that there's room for it to be greener. And then to the second question, what are some systems that failed? The kind of first-ish demonstration of factoring a number with Shor's algorithm was factoring sort of 15, and that's very easy to factor. You don't need a quantum computer to do that. But that was done on a so-called NMR, nuclear magnetic resonance computer. So these little molecules happen to have some qubits on them, and we just use that. And that was a great way to use what nature gave us, but was not scalable. The nature doesn't just give us sort of a really nice grid of 1 million spins. And so it turned out that was a technology that wasn't wasn't scalable.
There was a
Yeah, the question I have is like, how can like quantum computing like help us maybe explore space, or maybe set up like a space colony on, you know, the moon, or I don't know, Elon Musk's crazy idea, right? He wants to travel to Mars. And I'm not, to be honest, I'm not sure if he can. I don't think he has enough time to figure out how to travel to Mars.
So this is not a direct answer to your question, but quantum in space, I'm going to wax poetic about that for a minute. One way that we are having quantum interact with sort of the space industry is that there are satellites in space that have quantum information on them, and sort of beaming it from base stations to satellites, and from satellites back down to base stations. So classical networking uses a lot of satellites. Quantum networking, where we very similar but different and very important ways, also will make use of these satellites. I work on a project with Boeing Quantum for Space, Q4S, where they're sort of making one of these quantum satellites and shooting it up into space. So there will likely be some overlap, I think. So that's one thing. Another thing is that NASA, an agency that deals a lot in space, they have the Quantum Artificial Intelligence Lab, Quail. So they have lots of scientists thinking about how quantum computers can help the mission of NASA. Whether or not that directly, is relevant to making rockets more efficient, maybe we could do some sort of chemistry or materials discovery to find something that's lighter, or we could use a new rocket fuel, right? To design a new rocket fuel with a quantum computer. These are the types of questions we think about. But I'm probably not going to put a quantum computer on my rocket and let it do navigation in space. There's a quantum computer on or some quantum experiments on the ISS. One thing we haven't mentioned is that quantum systems can also be used for sensing. Very, very like quantum gravimeters that measure gravity. They can measure gravity much more precisely than any other known technology. These devices can help give us extra information. That's not necessarily computing. That's still using qubits and quantum technology in a different way to give us sensing of navigation, position, timing. Those are all things that can be accelerated by quantum sensors, which might help in a space-based mission.
On that note, with the other applications of quantum sensing and capabilities, I had this is one of these they say they've done it. No one else has been able to vet this, but China is working on quantum entangled radar systems. Are there other communications or sensing, or kind of you had mentioned the gravity detection that you see as hey, this still relies on some of maybe we need less qubits, or it relies on some of the technologies we're developing on the way to quantum computing, but it's hey, we can actually just use this right now directly.
Yeah, I'll take this one too. So, it's a great question. These requirements are different for computing and sensing, but they're all both built on quantum technologies. So, one thing that comes to mind immediately is a Costco can't really fit in my backpack, right? If I want to have this on the battlefield as a defense application, or I want to use it in the field, it really has to be miniaturized and it has to be ruggedized. There are companies that are doing this, and there are professors here who are also doing these things. And if we can get it down to say the size of a box truck, right? We can put these kind of quantum gravimeters, measure gravity, onto trucks, approximately the size of a truck, and we can drive those around and actually use it to sense the change in gravity from density changes underneath the ground. And why do I care about that? Because oil is not the same as rock, right? So I can actually sort of figure out, oh, I think there could be some gas, some natural gas, some oil, or just a cave or something below here. So let's dig a hole. So surveying with quantum gravimeters is one option. Another one which is often brought up is GPS denied navigation. GPS depends on satellites. Sometimes the satellites don't work very well. Sometimes there's an adversary who's jamming the signal, or sometimes you're just, you're on Lower Wacker Drive in Chicago, and you just don't know what's happening, and neither does your phone. So in that case, having an inertial sensor, so that measures an accelerometer, it tells you which way you're going with exquisite precision, can be used to figure out your vector of movement. And as long as you have a reference, you can then put that all together. And so you might imagine having a backpack with something that can tell you exactly where you are, without having to make any reference to any GPS type system. And there's another quantum sensing company that spun out of UW-Madison called Dirac Labs that is looking at this technology, and that came out of the engineering department.
What would a quantum program look like? What would an algorithm using quanta, how would it work? A typical classical program is like a series of yes and no questions, very elaborate, but still boils down to that. How would the qubits make a program go?
Yeah, so quantum programs look very much like normal programs. So if you look at normal programs, you have a sequence of instructions where each instructions changes the values of the bits on your machine in your memory. So it turns some zeros to ones and some ones to zeros, and some others are left intact. A quantum program looks very similar. You have a bunch of qubits, and they live in some space, in some superposition of zeros and ones, and some of them could be entangled. And each operation modifies these values. But just like Schrodinger's cat, you don't know what the values are until you look at it. So it's like typically a quantum algorithm looks like, you modify these qubits, you keep modifying their values, you don't look at them, and at the very end you measure them. That's what the operation is called, because it's kind of an experimental and probabilistic, meaning you could get a random value within some probability distribution. So it looks very, very similar to traditional programming, except of course, as from a programmer's perspective, you have to wrap your head around a lot of stuff. Yeah.
To be wrapped.
I think I'll just follow up very briefly. I think it's kind of the intuition for designing a quantum algorithm is very different and maybe doesn't exist. It's very non-intuitive, and one can sort of say things like, what you have to do is create an interference between the correct answers, and a constructive interference between the correct answers, and a destructive interference between the wrong answers, so that you maximize the probability distribution on the bit string you want to see. That doesn't make sense to me, but that's what Peter Shor says when he says how his algorithm works. So we may find, that maybe not my generation, but the next generation who grows up in a more quantum world and sort of learns quantum computing in high school and earlier, because these concepts are kind of dripping down, and there are programs from the Wonders of Physics program over in the physics department, and various other initiatives to sort of teach quantum earlier, at least have workshops and things. So these students, if they're coding quantum computers as their first thing, not in a graduate level program, we might find that there are different abstractions that make a lot of sense to them. Maybe not to me, but to them.
Okay. Yeah. I had a question for Oz. Earlier, you mentioned that with the rapid changes and developments in hardware, it's kind of made it difficult for software to advance. What is it about the developments in hardware and how there's many different types of quantum computers right now that makes developing software difficult?
I guess one aspect of the software stack at the very low level is the compiler. So the compiler takes your instructions that you write, that you're giving to the computer, and runs them on a computer. So it's translating between these two languages, and every time the underlying device changes, then it's roughly, you can think of it, it's a new language or a slightly different language with different constraints on what you can and what you can't say. So one of the things that we've been doing is trying to construct these compilers automatically, so that if the physicists across the street change their device tomorrow because they figure out a new architecture, a new technique, then I don't have to rewrite the compiler again. So it can just like automatically generate itself, if you will. Yeah.
Three questions actually. So first of all, the number of qubits is the number that gets a lot of attention, but isn't also the amount of time that you can maintain a superposition important? And what is that like if I had 10 qubits, which I could maintain for 1 hour versus 60 qubits, which I could maintain for 10 minutes? Is it the same? Question one. And what is the amount we get? What is the maximum superposition we have achieved? The second question, you mentioned Costco sized, but Microsoft made a lot of buzz about the Majorana one chip. So, what is the difference, and how viable is a chip-sized quantum computer? And the third is mostly, is there a chance for the public to come visit the physics quantum computers and see them and learn about them?
I do not have a lab. I'm a theorist, so but we can certainly ask the people who have labs what they could do. Yeah. To answer question 2, the Majorana 1 chip, pretty much all quantum computers, the qubit is small. It's that you need this large amount of infrastructure around it. And so a superconducting qubit is about a micron scale, which you can actually sort of see with your eye, or maybe you need a magnifying glass if your eyes aren't very good. Those Majorana qubits are sort of nanometer scale, and an atom, of course, is 1 atom. That's sort of angstrom scale. So those are really, really, really small. But you have to cool those Majoranas down to very, very low temperatures, and you have to put wires down to control them. And then, as it turns out, when we get to million qubit scales, we have these very complicated classical problems we have to solve alongside the quantum problems, like error correction. Those are going to require, you need another rack of electronics with a bunch of GPUs and FPGAs and ASICs. Those all have to be sitting right next to your device. So qubit is like this much area of Costco is used for actual qubits, and the rest is just cooling. It's lasers, it's wires, it's classical coprocessors that solve various problems. Yeah, I'm probably. Yeah, we'd have to work very hard to answer that question precisely, but back of the envelope, Costco. And then I think the first question, there are various ways to benchmark quantum computers. There's some number which is called quantum volume, which means you have to do 100 qubits 100 times, whatever. Keep it for 100 units of time, like you said, and that gives you some square. And those other options where you have 100 qubits for 10 minutes, for 10, or 10 qubits for 100 minutes, those are not square. Those are sort of rectangles in space-time. So it really depends on the application. It might be okay for me to have a sort of rectangle that goes for a very long time if I only need this sort of number of qubits to do the thing I want to do. Or I might need a lot of qubits for a sort of shortish amount of time. And it really comes down to the application, the algorithm, and various other parts of the stack. But anyway, the world record quantum volume is sort of 32-ish, 32 qubits that are fully entangled in 32 ways, something like this. They actually say it's 2 to the 32, but then it's sort of silly. It's a big number. You just take the log base 2 of it, so 32. But, there are people who have used 100 qubits and not fully entangled them, but still tried to do something interesting with those. And so that didn't give you this kind of square, but they were still trying to solve a problem with them.
I think we have to. You can, we have to stop. Sorry about that. Of course, our emails are on the website. So thank you so much for coming, and I encourage you to explore future events. You can either put your email as you walk out, or you can go to illuminatingdiscovery.wisc.edu and see what future events. In fact, the next Crossroads of Ideas event is coming up in January, and we'll kick off a 3-part mini-series on productive failure in science. It's never, though, in quantum science, right? And thank you again to Matt and Oz.